All right, in 8.4, we're going to be looking at another method for solving systems of linear equations. It's a streamlined technique, and the technique involves using a rectangular array, that's a new phrase for you, of real numbers called a matrix. The plural of matrix is matrices, and all of these, what you see, are matrices, okay? They're rectangular arrays of numbers, and they come from equations. I'm going to show you where they come from. The dimensions of a matrix is m times n, where m is the number of rows, and n is the number of columns, okay? The entry in the ith row and the jth column of a matrix is denoted by a double subscript, okay? You'll probably never use that, but that's how they do it. So if I say A1, 2, that means it's row 1, column 2. And whatever value is there, that's what A12 is, okay? Now, a matrix derived from the system of linear equations, each written in standard form with the constant term on the right, is called an augmented matrix of the system. Moreover, the matrix derived from the coefficients of the system, but not including any constant terms, is the coefficient matrix of the system. All right, so we're going to focus on the augmented matrix. That's what we really want to look at here. So it's really pretty easy to come up with. So here I have a system of equations in example 1, and I want to write the augmented matrix. This includes all the values, constants and everything, okay? So my matrix will be, I need to make sure in my system equations the x's are lined up and the y's are lined up and the constants are all lined up. Okay, so all I do is pull out the coefficients. So I say 2, coefficient of that y is 1, and the coefficient of 5 is, it's constant, 5. So on the second row, I do 3, -2, and 4. Now, instead of an equal sign in here, we put 3 dots. Okay, and that's just a clue that that's what the constant is in the system of equations. Now, example 2. Okay, oh, wait, we need to do dimensions, sorry. What's the dimensions of the augmented matrix? Well, how many rows do we have? We have 2 rows, and we say 2 by, how many columns? Well, we have 3 columns. You do count this column with the constants, okay? So here's my augmented matrix, and here's the dimension of it. Example 2, let's do this again. Double check that your systems are lined up, your x's are stacked. There's just 0x here, so don't let that mess you up. You have your y's together, z's together, and constants together. So I put 9, 0, 2, -25, -3, 11, 20, and -5. I put my little dots in there. Okay, now what are my dimensions? Well, I have 2 rows by how many columns? 4 columns. There it is. That's how you find dimensions. All right, so now in this part, it says write the system of linear equations represented by the augmented matrix. So we're really just doing that in reverse. Okay, and we're going to, this column is x, this column is y, and these are my constants. So I would rewrite this as 3x plus 4y equals 0, and then x minus y equals 7. Okay, so you can see we're just doing the reverse of what we just did. All right, in example 2, again, we write the system of linear equations. We have our x variables, y variables, z variables, and then the constants over here. So I'm going to have 0x, so I don't even write that in there. And then I do 12y plus 3z equals 0. Then I have -2x plus 18y, and I can leave the z part at 0, equals 10. Then I have x plus 7y minus 8z equals 43. So that's how I would write the system of linear equations that are represented by this augmented matrix. All right, moving on. There are 3 operations on an augmented matrix of a given system of linear equations that produce a new augmented matrix corresponding to a new but equivalent system of linear equations. The 2 matrices are row equivalent when one can be obtained from the other by a sequence of elementary row operations. Okay, we do all these row operations in order to solve for x and y and z, all right? But there's three operations we can do. We can either interchange two rows, okay, multiply one of the rows by a non-zero constant, just multiply through by something, or add a multiple of one row to another row. So these are our three tools in our toolbox that we can use to rewrite our matrix, all in the effort to solve for x and y. So we're just going to baby step our way through this. So this says fill in the blank using an elementary row operation to form a row equivalent matrix. So what I want to do is, this is my starting matrix right here. This is where it ended. I got to figure out what happened from the left to the right. What happened? Well, look at the top row. It's 1, 2, 3. Over here, it's 1, 2, 3. So nothing happened to my top row. It stayed the same. The bottom row, however, used to be 3, 12, 5, and now it's 0 something negative 4. So we got to figure what happened to this row right here to come up with this row, and then that'll help us find the missing term. So it doesn't look like I interchanged any two rows. I didn't just flip 1, 2, 3 and 3, 12, 5. That didn't happen. Did I multiply row 3 by a constant other than 0? Well, I can't multiply by 0 to get 3, so that doesn't work. I can't use that option. So number 3 is what's had to happen. I add a multiple of one row to another row. All right, so let's think about this. If I have a 3 at the bottom row, if I multiply to get to 0, I would have to add negative 3 or subtract 3. All right, so what did I do to get a negative 3 from this top row? Well, here's what I would propose we do. We take row 3, all our terms in row 3, and we're going to multiply everything in row 1 by negative 3. Okay? So let's see what happens when we do this. This is an example of option 3. We add a multiple of one row to another row. So when I take row 3 and subtract 3 times row 1, so let's just do this term by term. I would have 3 minus 3 gives me 0, and that's what I have here. The next term is 12, and I subtract 3 times 2, what was in the top row? Let's see. That's 12 minus 6, so that gives me 6. So I'm going to guess that 6 is what goes here. I'm going to know I'm right if I get a negative 4 in this last one. All right, so in the last term, I had a 5, and I'm going to subtract 3 times what's in row 1, which was 3. So that's 5 minus 9 gives me negative 4. So it's a little bit of a puzzle to figure out what operation did they do. Did they just flip them? Did they just multiply through by something? Or did they do the more complicated one, add a multiple of one row to another row? All right? So what we're going to do on these other two examples is the same thing. We're going to figure out what operation was performed to obtain the new row equivalent matrix. All right? Easiest way I know to do this is first look for similarities. Look at the bottom row, 2, 6, 7. The bottom row didn't change at all. So row 2, nothing happened. Row 1, look, it went from negative 4 to 1. It went from 8 to negative 2. And then from negative 20 to 5. So let's think about this. Let's see, can I multiply one of the rows by a non-zero constant? Is there something I can multiply through by? Well, okay, maybe if I multiply negative 4 times a negative 1/4, also known as dividing by negative 4, that would give me a positive 1. All right, if you're not sure, if you can't see it, try this. Put a variable in there, x. 8 times x equals negative 2. What happened here? Divide by 8 and simplify. Well, that gave me negative 1/4. So then does the same thing happen here? If I do negative 20x equals 5, if I divide by negative 20, I get negative 1/4. So what operation happened? Well, the way I would report this is I would say I would do negative 1/4 times row 1 is what happened. That's the operation that happened. Okay? Let's try example 2. Feel free to pause the video and try it on your own before I give it all away. So let's look at this. The first row in both of them are the same. Looks good. Second row, the same. Third row, not the same. So I need to figure out what to do. I went from a 5 to a 0, and I have to somehow I can't multiply through by 0. I didn't just flip rows, so I had to have added a multiple of one row to another. So let's think about this. The easiest multiplier is a 1. So if I multiply that first row by 5, I would end up with a negative 5 here. Negative 5 plus 5 gives me 0. So I'm going to take row 3, and I'm going to add 5 times row 1. Okay? So let's just trial and error here. So I take that 5, and then 5 times row 1 make it negative 5. That gives me 0. All right, that worked. Check. Let's try it with the next term. Row 3 was 4, plus 5 times row 2 would make it a negative 10. That gives me negative 6. That term worked. Okay, row 3 was negative 7. I add 5 times the third term, plus 15. That gives me 8. And then last term, negative 4, plus 5 times the first one is 6, plus 5 times that, negative 10, gives me negative 4. And that worked. So what happened here? This is how I would report what we did. We took row 3 and we added 5 times row 1. Now, you have to get used to it, and you'll have some trial and error, and that's okay. But you want to make sure that whatever operation you think it is, it works on every single term. So let's try this some more. Fill in the blanks using elementary row operations to form a row equivalent matrix. Okay, so it's the same thing again. Look and see what patterns you see. Top row stayed the same. All right, bottom row did not. So I went from a 2 to a 0. And I didn't multiply through by anything, and I didn't flip any rows. That means then I did something to row 3, and it had to do with row 1. So what could I do to row 1 that I could add to row 3 and then end up with a 0? Well, if I put on a coefficient of negative 2, multiply that by negative 2, that would give me a negative 2 up here. Negative 2 plus 2 gives me 0. So let's go with this theory and see if it works. So this would be 2 minus 2 gives me 0. That worked. So it would be 10 minus 2 times 4, which is 8. That would give me a 2. And then the last term would be 5 minus 2 times 6, which would be, 2 times 3, which is negative 6. And that gives me negative 1. So it did work. So what's the missing term? It's a 2. All right? So let's try example 4. It's a two-stage process, okay? We'll just take it in steps. Look, row 1 stayed exactly the same. And thankfully, it stayed exactly the same on these. And that's kind of a clue that you're going to use row 1 in each of your operations that you do. So let's see what happened. We went from a 3 to a 0 on that. Okay, so I took row 2 and somehow got it to 0. So what do I do to 3 to get it to 0? I subtract 3. So I need to subtract 3 times row 1. All right, so let's play this out. So that would be 3 minus 3 gives me 0. 8 minus 3 gives me 5. We're good. Let's do this. 10 minus 3 times 4, so that's 10 minus 12 gives me negative 2. And then we have 3 minus 3 times negative 1 is plus 3, so that gives me a 6. All right? Now let's do the last row. What happened to row 3 to get to 0 in that first term? Well, I had negative 2 here. I need to add 2 of row 1. Okay? So let's play this out. So negative 2 plus 2 gives me 0. 1 plus 2 gives me a 3. Good to go. We do 12 plus 8, because 2 times 4 is 8. That gives me 20. And then 6 minus 2 is 4. All right? So, that being said, let's look at this. Very interesting. Look, we went from here. Look, this third row stayed the same. 0 and 3 didn't change. That means the whole row stayed the same. So just copy them over. But now we got to figure out what happened to row 2 to go from 0 to 1. And then we got to figure out what's going on here. Well, really all you have to do to get that 5 to a 1 is you could divide by 5, right? Or multiply by 1/5. So 0 times 1/5 is still 0. 5 times 1/5 is 1. -2 times 1/5 is -2/5, and that's okay. 6 times 1/5 is 6/5. And so you can see the progression of what happened here. We got leading zeros in our rows, and that's what we wanted. Okay, so we're going to pause here and do the rest of the notes in a separate video. We'll tackle row echelon form there.